In this microscope slide, you can see a cell with bubbles sitting against its membrane. When the ultrasound exposure starts, you can see the bubbles vibrate, and they're vibrating against the cell membrane. What you see is if you have a fluorescent dye that you're trying to get into the cells, that it only gets in to the cell across this membrane here, where this bubble is actually sitting on the membrane. You can see here the red dye that has got into the cell, but just at that point. You can see that here in static images, where the membrane of the cell is here, the bubble is sitting here, the bubble is oscillating, and you can see the dye comes in between these two oscillating bubbles here. And slowly that dye, the intensity of the dye, decays over time. But that's a way of getting drugs or other molecules across the cell membrane safely, with the membrane is still intact. Now, apart from the cellular effects, we know that there are effects on blood vessels. We see platelet damage, we see hemorrhage where the blood vessels are damaged, we see constriction of vessels, and we see permeability of the blood vessel wall. So here you can see an example of blood vessel damage. Again, this is an electron micrograph. You can see here that the endothelial surface of this blood vessel has been damaged by an ultrasound exposure. We know that ultrasound exposure of blood vessels in the presence of bubbles, whether these are acoustic cavitation bubbles or introduced contrast agent bubbles, can have effect on blood vessels. You can see here the results from an experiment in which we exposed isolated rat mesenteric vessels to ultrasound with and without contrast agents. Along the top you can see the measure of cavitation activity, and here you can see the images of the blood vessels under a microscope. In the first column you can see our control vessels, where there's obviously no ultrasound cavitation, and at the bottom you can see the histology, very nice cross-section of a blood vessel with no damage. In the next two columns you can see ultrasound exposure in the presence of ultrasound contrast agents, and what you can see is not only can you see a cavitation activity, but you can see that when we put dextran into that vessel, that dextran is permeating through the vessel wall to allow us to see it under the microscope. So in this case we have a lot of dextran coming through the vessel wall, being obvious, and here you see a bit less at the lower acoustic pressure. You can also see damage to the endothelium under histology. In the last two columns we have no ultrasound contrast agents. You can see vessel damage due to the ultrasound exposure on histology, but we're not seeing that enhanced permeability, that permeability change. You can also occlude the blood supply using ultrasound, and here you see an example. Here we have an angiogram of a rat. You can see the heart up here, you can see the femoral vessels here. We tried to occlude this left femoral vessel, and with a single shot of ultrasound you can see that we've here occluded the vessel and stopped the blood supply. This has applications, for example, if you want to destroy the shunt vessel in twin-twin transfusion in fetal medicine. I've listed here the known biological effects, and I've only really touched the surface of the sort of biological effects we might expect. But here you see the same list, but color-coded. So the effects that we know cavitation is involved are in blue. Those we know are thermally mediated are in red. Some of them, of course, are both thermally and cavitationally mediated. But here you can see roughly what we're getting. So in summary, we know with ultrasound that we get heating. We can use that in physiotherapy for example, helping in tendon injuries. We can use it for thermal ablation if we go to temperatures of above 56 degrees centigrade. We can use it for hypothermia, where we use ultrasound heating in conjunction with radiotherapy plus chemotherapy. Or an area that I haven't really touched on is if you put your drugs in a liposome which has a low melting point, you can use your heat to melt the liposome at the site which you want the drug delivered. So you give your ultrasound locally, you give your liposomes systemically. And when you get nonlinear propagation, we do get enhanced heating. But we get this heating effect whether we have nonlinear propagation or not. We also get cavitation effects, and these may be due to collapsing bubbles, to inertial cavitation, may be due to stable bubbles, the ones undergoing breathing oscillation. Or it may be due to the contrast agent microbubbles that we introduce into the vascular supply, into the blood supply. They're used commonly for imaging, for enhancing images, but we can also use them for therapeutic advantage. Where we have collapsing bubbles, we know we get enhanced heating. The collapsing bubble will increase the amount of energy absorbed. We know we get membrane permeability changes, and collapsing bubbles are used for stone destruction in lithotripsy. With stable bubbles, the primary thing that happens is that we get membrane permeability changes, which allows us to enhance drug delivery. And with the contrast agents, we can increase the amount of streaming we get. So we have an existing microbubble, we can use the streaming around that existing microbubble, for example, to dissolve clots. We can use those bubbles to open the blood-brain barrier because we know that we can change the permeability of blood vessels, and we can change the permeability, for example, of tumor vessels to enhance drug delivery. There are other effects that I haven't touched on, which I class as radiation pressure and others. These are very much less well studied than heat and cavitation. We know that associated with an ultrasound beam is a radiation pressure effect, and that will displace tissue and may cause very subtle effects, which, for example, may be the reason that we know that we can enhance fracture healing with ultrasound, with very low levels of ultrasound. You can see increases in extracellular spaces in tissue at low levels of ultrasound, and disruption of the extracellular membrane. And it's thought that these are due to radiation pressure effects. And radiation pressure can be used in lithotripsy as well to move the stones around, for example. Thank you very much.